Lately we've been talking about interference. It's a simple enough phenomenon. If you have more than one source of light, you add their fields at any point in space to get the net field, and sometimes the sources add up in such a way to make the net field big, and other times they add up in such a way as to cancel. It's a simple enough phenomenon, in fact, that you might be kind of wondering why we never ever see it in regular life. How come adding one flashlight beam to another flashlight beam never gives you interference fringes? Well, that's where the notion of coherence comes into play. If your flashlight beam really did represent a pure sine wave, it would absolutely interfere with other flashlight beams. But it isn't a pure sine wave. A flashlight beam comes from a little filament, and a filament isn't a point source. There are lots of atoms in that filament, all radiating, and the radiation from one atom is generally not at all correlated with light from some other atom. They might all each individually be making sine waves, but they're not in phase with one another, so the overall beam is a mishmash of a bunch of bits of light with random phase relationships, and it all kind of washes out into a big blur. What we've drawn here is spatially incoherent light. Light such that bits in one location are uncorrelated with bits in another location. If you're not used to using the term correlation, basically two things are correlated if knowledge about one gives you knowledge about the other. Two pure sine waves, for example, are generally going to be strongly correlated with one another, even if they're out of phase. If you know you have two sine waves, and one is out of phase with the other by some amount delta, then knowing the value of one at some point lets you figure out the exact value of the other one at the same point. And strongly correlated light will exhibit interference. As you vary that phase angle delta, the net result will go from bright to dark and back to bright. But if you've got a bunch of sine waves that have all sorts of phase relationships, then knowing what one is doing doesn't tell you anything about what the others are doing. And if you start varying the phase relationships there, nothing about the net result will change. Uncorrelated light does not exhibit interference. There's also something called temporal coherence. Go back to that light bulb filament. Any particular atom in that filament is making a sine wave. Except that isn't pure either. That atom is hot and bothered and is getting jostled around, and the photons it emits now aren't necessarily in phase with the photons it's emitting a moment from now. This light is temporally incoherent. And most real light is pretty damned incoherent spatially and temporally. But no light is ever perfectly coherent or perfectly incoherent, so let's see what we can do about quantifying coherence a little bit. Take a sine wave that has phase jumps from time to time, a temporally incoherent source. Let's split that wave into two identical waves and see if we can interfere them with one another. If there's no relative phase between the two sources, they definitely interfere constructively. Peak to peak, trough to trough, all along the length, they add up. So now let's slide them out of phase by half a wavelength. They mostly interfere destructively. Trough to peak to trough, over most of the length, though near the discontinuities, there are some mismatches, places where the interference isn't destructive. Averaged over the whole length, then, we get something that's mostly but not completely dark. And if we slide them way out of phase, we get to where any points on the two waves are just as likely to add up constructively as destructively, so the average over the entire length isn't either. It's just kind of a middling half-bright. Kind of like what you get when you actually combine two flashlight beams. So there's a characteristic coherence time and coherence length here. If some light is experiencing phase resets roughly every tau seconds, the coherence time is roughly tau, and the coherence length is roughly tau times the wave speed. If you have two sources with some coherence time tau, and they're within tau of being synced to one another, they'll show some noticeable interference. As you slide the one with respect to the other, the net result will vary between bright and dark. But if these sources are out of sync by more than tau, all the interference effects will disappear. This sort of thing is really important in interferometry. You may recall good old-fashioned Michelson interferometers. You have an incoming beam of light, it gets split in two, and then recombined. By varying how far the one half of the light travels with respect to the other half, you can control the phase relationship between the two beams, and rig it so that you get a bright output or a dim output. But that only works if your input source is sufficiently coherent. You can feed a flashlight beam into a Michelson interferometer all day long, and you'll see no interference at all. But take a helium neon laser, which often has pretty long coherence lengths, and you can vary that path length quite a bit and see nice, clean interference. Diode lasers, like laser pens, are kind of in between. They've got pretty short coherence lengths, but not so bad as a light bulb. While I've never tried this personally, my understanding is that you can feed a diode laser into an interferometer and get interference over short changes in the distance, comparable to the coherence length, but it falls apart pretty quickly. As a fun aside, true holograms involve recording interference patterns onto super high resolution film. As such, that requires coherent light to do. Since highly monochromatic lasers are the easiest way to get coherent light, that means the easiest way to make a good hologram is to do one in a single color. To sum up, a light wave such that spatially separated points in the wave are correlated with one another is said to be spatially coherent. A light wave such that temporally separated points in the wave are correlated with one another is said to be temporally coherent. The more coherent a source of light is, the more likely it is to exhibit interference effects, and the more robust those effects will be. Further quantitative analysis of these ideas is at the heart of what's called statistical optics, which we'll reserve for later.